Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. To close out 2018 and open the new year, we're excited to present to you our first ever AI Rewind series. In this series, I interview friends of the show for their perspectives on the key developments of 2018, as well as a look ahead at the year to come. We'll cover a few key categories this year, namely computer vision, natural language processing, deep learning, machine learning, and reinforcement learning. Of course, we realize that there are many more possible categories than these, that there's a ton of overlap between these topics, and that no single interview could hope to cover everything important in any of these areas. Nonetheless, we're pleased to present these talks and invite you to share your own perspectives by commenting on the series page at twimlai.com/rewind18. In this episode of our AI Rewind series, we introduce a new friend of the show, Simon Osindero, staff research scientist at DeepMind, to discuss trends in deep reinforcement learning in 2018 and beyond. We've packed a bunch into the show as Simon walks us through many of the important papers and developments seen this year in areas like imitation learning, unsupervised RL, meta learning, and more. Enjoy. All right, everyone, I am on the line with Simon Osindero. Simon is staff research scientist at Google Mind. Simon, welcome to This Week in Machine Learning and AI.
Hi, Sam. Good to chat with you.
Awesome. It is great to have you on the show. So you are joining us for our end of 2018, beginning of 2019 kind of reflections and predictions series. And you're unique in this series in that the other guests that we've featured in the series are all kind of guests that are returning back to the podcast, but you are our new guests in this series. But we wanted to catch up with you because we've been trying to get you on the show for a while. We just saw one another at NeurIPS, and this seemed like a great opportunity. For our project here, we're going to talk through some of the interesting developments in your particular area of focus, which is deep reinforcement learning. But you've identified a bunch of papers that caught your eye as being significant this year.
Yeah, that's right. I guess when you asked me this, I was kind of trying to think of what was interesting, and just the rate of publications at the moment is so high that given that and the number of subfields that I see developing in deep RL these days, it was kind of hard to come up with a short list. So I figured maybe what we do is touch on a couple of high level topic areas, and I'll try and pull out from each of them a couple of the papers that I thought were interesting or that caught my eye. Actually, even doing that, there's probably going to be some focus areas that we could touch on that I don't think we'll have time to, but maybe we'll do that in another show.
Awesome. So what's the first area you have for us?
So the first up is what I'm going to call grouping together sort of imitation learning, learning from demonstration, warm starts, and curricula. So kind of this idea that we don't always need to learn from scratch without any information. And in fact, doing that when rewards are very sparse is kind of difficult. And so we can leverage other types of knowledge. So in particular, maybe demonstrations, a small number of demonstrations from other agents. Some of those might be humans. Another way of thinking about this problem is to think about curricula. So either over problems or model complexity, and essentially starting off doing something simple and then bootstrapping from the solution to a simpler problem to a more complicated one.
With regards to imitation learning, I typically see this in the context of reinforcement learning. Are they linked inseparably, or can you do one without the other?
Yeah, I mean, for sure you can do reinforcement learning without imitation. And actually, I guess depending on what you mean by imitation, you don't necessarily have to do it in a reinforcement context.
Are there examples that come to mind of imitation learning outside of the reinforcement learning context?
I mean, I guess depending on how you think about it, you can actually imagine even some of the kind of the way in which we train some language models is essentially being imitation learning, the kind of like sort of teacher forcing aspect of sequence model learning. You can kind of view that as a kind of imitation.
All right. So the first paper on your list of important papers in this space comes out of DeepMind. It's the playing exploration games by watching YouTube paper. And actually, by the time this interview is published, my interview with Nando de Freitas, one of the authors of that paper from NeurIPS, will have been published. So folks can take a listen to that one.
Great.
Yeah, were there? What were the highlights of that paper for you?
I guess a couple of things, and I'll since Nando's already chatted about this, I'll be relatively brief. But it's kind of nice that we have observational demonstration data rather than necessarily providing. So I guess there's a couple of ways that you could give an agent demonstrations. One is just letting it watch another agent and observing the world. The other is kind of literally telling it action sequences that another agent have done that have been successful. And so this is a kind of nice example in that it's purely observational. And so, the hope is that by sort of like generalizing this technique, we really could take it from, in this case, it was looking at a video game, but you can imagine wanting to scale this up and just having an agent watch people doing stuff on YouTube and learn to do stuff in the real world. Mm-hmm. So it's kind of got a lot of potential in that direction.
Okay. Cool. How about the next paper on your list?
So the other one was another DeepMind paper and similar kind of idea. So this is the Observe and Look Further, Achieving Consistent Performance on Atari. Okay. And again, it's using demonstration. In this case, they do get to see the actions, but they basically learn to get good performance on some of these hard exploration games with just a single demonstration trajectory. And the kind of idea there is that you basically, in your replay buffer, you have the experience that the agent's generated, but you also get to populate that with experience that a demonstrator has provided. And it turns out that if you do that and a couple of other tricks in terms of how you do the training, you can also get extremely good results from a very limited amount of demonstration data.
So when you say a single, did you say demonstration trajectory?
Yeah. So imagine a video game just kind of playing through it once, and that's all you get to see. So the reason that's kind of interesting is that a single I guess it depends on the game, but a single playthrough wouldn't necessarily capture all the variability that you get when you're playing the game. If you start to do things a little differently at the beginning, then things can kind of diverge. But in this game, and I guess it's true of a lot of environments, if you're starting from scratch and you don't know anything, then there's lots and lots of things that you could end up doing. And so even just seeing one demonstration of roughly the right thing to do can be extremely helpful.
How was the imitation part of this paper approached?
So like I say, they're using they're building on a technique DQFD, so DQ learning from demonstration. And so the idea there is you have this replay buffer, which is basically transitions that you've seen in the world. So you have your current state, the action you did, where you ended up next, and the associated rewards. And in regular Q learning, or you would essentially populate that buffer just with your own experience. And so when you're starting out, you maybe don't really know how the world works. And so it's part of the reason that this is interesting and kind of why sort of highlighting this as an area is there's a lot of problems where just getting the agent off the ground and starting to do something simple can actually end up being the hardest part. But once you're starting to see rewards and kind of figuring out how the world works, then learning tends to kind of progress reasonably. So in terms of learning curves, a lot of the time on some of these tough environments, you'll basically see it flatlining for a very long time because, the agent is essentially just randomly exploring until it figures out something interesting, and then it starts to get a signal that it can learn from. And so, I think that's another reason why just a very small amount of demonstration data or instruction or just something to kind of kick learning off the ground can end up accelerating learning and help us learn on problems that otherwise would be very hard to do from scratch.
Were there other papers in this category?
Yeah. So there was another one that we had at NeurIPS ourselves, actually. So this was kickstarting deep reinforcement learning. And that's a slightly different approach. So it's not using demonstrations per se anymore. The idea is we have a pre-trained teacher agent. So you could imagine getting that in a couple of different ways. So maybe that would be a simple, easy to train agent that doesn't necessarily get the best performance, but is easy to train in a reasonable time. Or maybe you have lots of different tasks in an environment you want to do, and you might be able to have a teacher that specializes on a single task, which is typically easier than learning a whole bunch of things. But you have a student who wants to be able to learn to do many different things. And the approach we have there is we are able to have the student experiencing the world, and we can also query the teacher and essentially ask, what would you do if you were in this situation? So here we have access to the actions, and the idea is we'd like the student to match the teacher's behavior, but we don't just want to end up completely copying the teacher, because there'd kind of be no point in that. So we also have a mechanism that essentially over time allows the student to figure out how much attention it should pay to its teacher and how much attention it should pay to its own experience. So over time, the student trusts its own experience more and more, listens to the teacher less and less, and so you can end up with a student exceeding the performance of the teacher. And we kind of see this as being useful in a couple of different ways. So particularly right now, in terms of the kind of nuts and bolts of experimental cycles, you often want to try out a lot of different ideas and architectures. And if for each one of those you're having to start from scratch each time, that can be costly in terms of computation, but also can just be slow. So we kind of see this as a nice way to shorten experimental cycles if you're wanting to iterate through different agent architectures pretty quickly. Another benefit that we see is sometimes, if you have a really big agent, it's just, it's a lot of parameters to train. And so getting that off the ground initially can be kind of hard. And so we've actually seen really nice progress taking very simple agents that are quick to train, but they flatline at not great performance. But by having that as a teacher, we can then get one of these much, much bigger agents off the ground that then ultimately gives us much better performance. So it's, as a technique, it's something that we're using quite a lot internally.
One of the contexts that you explained this in is in terms of like multitask, or at least an agent trying to learn multitask. I don't know if it's formally multitask learning, but what's the role of the teacher in that multiple task scenario?
Yes. So in that scenario, it would be often what we'd like is a single agent that can do lots and lots of things. And that training that from scratch can be kind of challenging. What's often more manageable is if you kind of subdivide the problem space into smaller and smaller chunks. So you learning to do just one of those tasks, or maybe even breaking a single task into smaller chunks. So learning to do a small part of the overall problem, you can get a teacher agent that specializes on that little bit of the overall problem space. And if you then have many different teachers that specialize in different parts, between them, they're able to do most of the things you care about. But like I say, what you'd really like is a single agent that has competency to do everything in the domain. And so in a situation like that, you could build these simple agents that kind of specialize in parts of the problem space, and then use those different teachers to then transfer their knowledge to a student that is learning from all of them. And as I say, over time, it can figure out how much attention to pay to the different teachers and get good performance. So in the paper, we have a set of different tasks that we want to do in the 3D DM lab environment. And so, they're kind of like navigation kind of tasks, avoidance kind of tasks, gathering tasks, all sorts of things like that. And we have teacher agents that are specialized for each one of those. And then we can build, but what we're really interested in, and this is, kind of moving towards general intelligence, we really want one agent that can do lots and lots of things and can also learn to do new things. And so one way of getting that off the ground is to have these simpler, less general agents that specialize in particular parts of the problem space, and then distill their knowledge into the student to get the student off the ground.
To be clear, so maybe an example, if you say you have, you're trying to train an agent and you've got 4 kind of things that you want it to learn, and you create 3 of these teacher agents. Are the teacher agents increasing performance in the three categories for which you have teacher agents, or is the lack of a teacher agent allowing the agent to learn more about the one where you don't have a teacher agent?
In this setting, I guess it's a little orthogonal to that. In terms of the teacher should never be too limiting, in the sense that we have this mechanism. In the paper, we're using population-based training, but you could imagine doing other things that essentially tries to meta learn how much attention to pay to the teacher. So if the teacher is useful, if it's giving you learning progress on the thing that you care about, great. As that becomes less and less useful, you pay less and less attention to the teacher.
Yeah, so far in these conversations, what's been interesting is that I could, spend the entire time talking about one thing that kind of pulls me in that direction, but we'll try not to do that here. And so were there other papers in this category? Or do you want to move on to the next one?
So we had another paper, mix and match agent curricula for reinforcement learning. And there, rather than having a teacher that's kind of pre-trained, it's kind of as if you have you think of it as a sort of like companion agent that is trained jointly with the one you really care about. So in practice, how we implement that, we have a mixture policy. So which is two different policies that we kind of blend together. And the idea there is maybe a much simpler policy would be easier to train. So imagine something that has far fewer possible actions that it could take. And so often that's simpler to learn. But what we'd really like is an agent that has access to many, many actions. One thing you could do is initially train an agent with few actions and then use the behavior of that agent to train the one that has many, many actions. And in this particular setup, we do that in a continuous way where the learning is shared between both different types of policy. And we have a term that essentially encourages the information to flow from in a sense, the simpler and faster learning agent to the complex, more slowly learning agent. And again, how that process is orchestrated is done automatically with this method, population-based training, which essentially tries a whole bunch of different values for how strongly we're coupling the behavior, and preferentially follows the ones that are giving the best empirical performance.
So the next category that you identified was what?
So this one is, I guess, what I call unsupervised RL, or you could think of it as self-supervision or different kinds of interesting auxiliary tasks. So I think this is sort of a general direction that lots of people are interested in, which is the information in a reward signal probably isn't enough to train the scale of agents that we're interested in a reasonable amount of experience. It's not very information rich, but there actually is a ton of other stuff in the environment that we can learn from. And so leveraging that along with the reinforcement, with the reward signal, is something that's, I think we're going to see a lot more. So you've probably heard Jan LeCun talk about, the kind of the cherry analogy with a cake. And
Mm-hmm.
So it's kind of getting at that, but it's sort of, the point is that there's all sorts of things that we can learn from in the reinforcement learning context. And so examples of this, not from this year, but previously, would be the kind of Unreal paper where you're essentially doing a whole bunch of auxiliary prediction tasks in addition to trying to learn the policy and value. One of the papers from this year that I thought was particularly interesting in that sense is this one, unsupervised control through non-parametric discriminative rewards. And the basic idea is it's wanting to kind of learn to discover and achieve goals without any supervision. So it appears to be similar to what happens if you have like a young kid. You're essentially just learning what you can control in the world, learning what you can do, but no one's necessarily. You do have some supervision, but a lot of learning is just figuring out, what can I affect? What can I control in the world? Can I set myself arbitrary goals and then achieve them? And so it's kind of taking a shot at that problem. Does that kind of make sense?
Yeah. How did they kind of encode that knowledge that they're making not relative to the loss function?
Yeah, no, that's a great question actually. So they actually learn a loss function. So there's a couple of clever tricks that they do. So you start out behaving, let's say randomly, and you know that states that you visited in that random behavior are achievable, or something close to that should be achievable because you've achieved that before. So this is drawing on some of the ideas from there's a paper last year on hindsight experience replay, which essentially is maybe I was trying to do one thing, I didn't necessarily do that, but I did a whole bunch of things, and so you can kind of learn about the counterfactuals. When you're acting, you do something, and so learning about what you did is an alternative to learning about what you wanted to do.
Mm-hmm.
So that's kind of one element. The other element is how you figure out how well you've achieved those goals, and they use an approach that's a little similar to the discriminator in a GAN. So that the basic idea is, the three components. You have a goal condition policy. So you have a policy that gets to see its current state, and it also gets given a goal state that it's trying to achieve. And under ideal conditions, you kind of plug both those in, and it will get you to the goal. But then there's the question that I think what you're saying initially: how do you figure out if you've achieved your goal or not? And that's where this sort of bootstrap teach comes in. So the idea is, imagine the goal that I'm trying to achieve, and imagine a whole bunch of other possible states that I could be in. So there's the target and a whole bunch of distractors. What I'm going to do is try and learn a classifier that distinguishes between those distractors and the goal that I was trying to achieve. And the way that that's trained, it's a little subtle. So there's two things that we can plug in there, because if you follow what I was saying, you might worry there's a bit of a circularity. So one of them is to plug in some of those hindsight goals. So given some initial state and just a random trajectory, there'll be states that I go through. And so I could, after the fact, say, hey, that state that I ended up passing through, that was my goal. And so the nice thing about that is you know that you achieved it because you were literally in that state. So you can use that to kind of get this classifier a little off the ground. Now, other data that to distinguish between that goal that you reached and these distractors, but then it's also bootstrapped a little bit, and there you essentially end up saying, wherever you got to when you were following this particular goal, I'm going to treat that from the point of view of the classifier as if that was the ground truth, which sounds like it might be a little unstable because initially you're not going to be achieving those goals. But what that ends up doing is it sort of gives you a scoring function that is kind of smooth in the sort of meaningful space of task achievement over time. So, I don't necessarily need to be pixel perfect to say that I've achieved that goal, and there might be different ways of achieving the same thing. And so by plugging the agent's behavior in that way, they're able to learn an intrinsic reward function that is effective at kind of critiquing how well they achieve these arbitrary self-derived goals. Yeah. So I think that this kind of area of self-supervision or unsupervised RL is going to be something we're going to see a lot more of, kind of figuring out good ways of how we can set prediction or control tasks for ourselves in order to expand the knowledge and capabilities of an agent in a particular environment.
And so is this general category, is it trying to help us overcome the difficulty of creating loss functions for RL?
Yeah, you could view it as doing that in one way. So in terms of a lot of problems that we might be interested in, so imagine, a kind of robotic control problem. We're sort of trying to move away from hand engineering reward functions. So, in that setting, you might, what you really care about is the task done or not? But just training on that is very sparse. So, you basically get to know if you've done the task or not pretty much at the end. And there might be lots of different ways of achieving that. And to the extent that you try and hand design a reward function, you're also, in some sense, hand designing a solution, which we're kind of trying to get away from. If it was easy for us to design a solution, then maybe we wouldn't need to learn it in the first place.
Right.
So, yeah, this is kind of heading in this direction of how can I build a system that can learn to control the environment in lots of different interesting ways. Because if I can do that, then when you give me your problem, if I know how to do all sorts of things, then essentially when you give me your problem, I just need to figure out, of all the many things that I'm capable of, which one is the one that fits your particular problem. And so that then becomes a lot easier.
So what's the next category?
So the next category, learning to learn or meta learning. So this idea of how do we use learning to improve the process of learning itself? And I'd sort of, this kind of blends in a little bit, especially in the RL setting, with how do we learn to acquire experience that is useful for learning on tasks we care about, which is more or less exploration. So I had 3 papers from this topic that I thought would be good to highlight. So the first one is called Meta Reinforcement Learning of Structured Exploration Strategies. And there's a couple of elements to it. So it builds on some meta-learning ideas from previous papers. So there's a paper, Model Agnostic Meta-Learning, MAML, that folks might have heard of, where the idea there is you're trying to find model parameters such that given arbitrary new problems, you can rapidly adapt to solve them. This one is building on top of that, and you have a policy that has latent variables. And in this case, those latent variables are going to add sort of episode scale noise or stochasticity to your behavior. But there's other ways you could do that conditioning. The point is there's a latent variable that different settings of that cause your model to cause your agent to behave differently. And so by setting those parameters, you effectively can get different types of exploratory behavior. So they essentially try to learn an initial distribution of these latent variables such that for new problems from the domain of interest, if you sample from that, you quickly produce behaviors that allow you to gain experience, that allow you to solve those new problems rapidly. So you're, rather than sort of like having to have stochasticity at each time step, you get to explore in a structured way across the scale of an episode.
Okay.
So that was one of the ones. Another one, this paper, Evolved Policy Gradients. And there it's very, very similar meta-learning flavor. There the idea is, can we evolve a reward function, so an intrinsic reward function, such that if I optimize according to that reward function, I get good performance on the task that I care about. So again, imagine one of these settings where you basically, all I care about is, did you do the thing that I wanted you to do or not? Did you complete the task successfully? And as we were saying before, hand designing, a dense reward function that tells you, for each state action transition, how good was that? It's kind of hard, but maybe that's a function rather than specifying it. Maybe we can learn that function, and that's what this paper is trying to do. And it's using evolutionary methods to do that. So you basically you have an inner loop where you're using regular policy gradient learning, and an outer loop where you're using evolutionary search to figure out what a good function would be. So I plug in a function, you get to train with that function. I see how well you did training with that reward function, and I'm slowly shifting my search space of functions towards ones that, when I optimize them, give me good performance on the thing that I really care about.
The Evolved Policy Gradients paper is out of OpenAI, and the Meta Reinforcement Learning paper, if I remember correctly, is out of Berkeley.
That's it, yeah.
Okay.
I actually think both of them, they might be both the OpenAI Berkeley collaborations, but...
Oh, really? Okay.
Yeah.
Okay, interesting. Yeah, the meta learning space is a really interesting one that I'm starting to hear a lot about. Yeah.
I think there's a ton of interesting potential there. The other paper I was going to mention in that topic real quick was, this one is another DeepMind paper, Meta-Gradient Reinforcement Learning. And yes, similar themes again in terms of having sort of 2 scales of optimization. Here we're asking ourselves, there are parameters that essentially influence the return that we're learning on that can affect learning dynamics. So the discount, how much I discount rewards into the far future is a property of the algorithm that affects learning dynamics. So even if there is a horizon that I truly care about, it might be the case that I get better empirical performance by using something that's different from that. And so this paper is combining regular policy gradient with essentially a second set of rollouts that try to, again, ask the question, if these meta parameters of my learning were different, would I be making better learning progress? And so it's a way, for instance, of automatically and dynamically tuning things like the lambda and TD lambda or your discount. Moving on, and I'll try and condense this section a little bit, since we're probably going to get tight on time if we kind of go into a lot of detail.
I'm trying to hold back my many questions here.
So yeah, another kind of interesting area is exploration, learning to explore, and sort of dealing with different types of uncertainty. So I guess you can think of two types of uncertainty. And so folks lately have been talking a lot about sort of epistemic versus aleatoric uncertainty. So epistemic uncertainty is basically represents your lack of knowledge or data about the world. So it's like uncertainty in your model parameters. Whereas aleatoric, you can kind of think of that as like fundamental randomness in the world. So stuff that you just can't predict no matter how much data you see. And maybe that's because it's truly random, or I guess other people might argue that those are things that are just kind of outside the capability of a model class, but it kind of boils down to the same thing. So yeah, there's a couple of papers that are closely related actually that touch on this. So there's a really nice paper at NeurIPS, Ian Osborne, Jonas Lenides, and Albin Casero, randomized prior functions for DeepRL. And there's a couple of really nice tricks in what they do, and this is also kind of building on prior work that I've seen reused in a couple of different places. So this notion that we can use a sort of bootstrapped ensemble of functions to try and represent uncertainty. So that's basically just rather than having a single function, if I train lots of copies of a function with different initializations and with, in this case, different priors, which I'll touch on briefly in a second, I can then look at to what degree the different models in the ensemble agree or disagree. So if there's a lot of variance in the model's predictions, then in some sense that's a reflection of uncertainty. And it turns out you can kind of make that connection tight under certain conditions. And in general, it seems like a good heuristic. So the idea here is we're going to do that with our Q functions, and then build on top of that for learning. The notion of the randomized prior essentially boils down to I'm going to have a prior distribution over parameters of my function class, and for each member of the ensemble, I'm going to sample from that prior, and instead of effectively doing weight decay towards 0 as a kind of regularization, I'm going to do weight decay towards those initially sampled parameters. You can kind of think of that as starting off with some random function from your prior beliefs, and then learning a correction function on top of that to model what you actually see in the world. And so it turns out if you do that and you do it in the right way, you can basically sample, when you're acting, you can sample a function from your ensemble, act according to that, gather experience, put your experience in a buffer, bootstrap, update all the different members of the ensemble, and it deals with that uncertainty about the world in the right way that leads to good exploratory behavior. So yeah, I thought that was a really cool paper. There was another paper, I think OpenAI and University of Edinburgh folks, so Yuri Berta, Harrison Edwards, Amos Storkey, and Oleg Klimov, exploration by random network distillation, that take a similar sort, or you can actually draw a fairly tight connection between what they do and the paper I just described, although it's maybe not so obvious immediately. What they're doing is they're coming up with a function that so you have a random function, and what you're going to try and do is predict the outputs of that random function using a function that you're learning, and you're going to use your prediction error as a sign of unfamiliarity. And then you get to plug that in as an intrinsic reward. So the idea being, if you're in discrete states, then you can use some kind of count-based measure of how unfamiliar you are in a certain part of the world and kind of give bonuses for exploring new places. That gets harder in much bigger state spaces where you can't enumerate everything. And so this is a kind of another way of approaching that. How do I measure how uncertain I am about this part of state space? And so, so essentially what you do, you have this random function. You're trying to learn something that predicts the outputs of that random function when applied to the state, and your prediction error you're going to use as an intrinsic reward. So places that you visited lots and lots, you kind of know what how that random function is going to behave there, and so you should have relatively low prediction error. Places that you haven't visited that much, you're going to have a higher prediction error, and so you'll be incentivized to go find those and explore those more. And so they use that approach on Montezuma, which is this hard exploration game, and they get some really nice results using that.
Is Montezuma still considered to be, unplayable, with high performance by RL agents, or have we kind of cracked that with this and other recent agents?
Yeah, I mean it's still pretty challenging, but yeah, with approaches like this and other recent agents, I think in this paper they get superhuman performance.
Okay.
Yeah.
Okay, interesting. So these are all ways to kind of structure the exploration space and kind of create different types of ensembles and train across those ensembles.
That's right. Yeah.
Okay. Oh, very cool.
And then the other one that I guess I'll just mention briefly that is sort of in that category, but in some sense is dealing with the other type of uncertainty, was a paper, Implicit Quantile Networks for Distribution RL. That was Will Dabney, Georg Ostrowski, David Silver, and Rem Munish. And it's sort of building on some of these previous ideas in distributional RL, where the idea is, rather than just predicting the expected return, I'm going to try and predict the distribution of possible returns. And so, that could happen. If there is sort of intrinsic uncertainty in the environment, then even if I'm following the same policy, how the world turns out could end up having variability in it. And rather than just kind of model the mean of that, you can also try and capture properties of the distribution. And that's potentially interesting for two different reasons. One, it's a richer prediction problem. So you can sort of think of predicting that distribution as helping in the same way that auxiliary tasks do. And then the other is having those sorts of estimates are themselves useful in some cases. So, if you want to be risk sensitive, for instance, then you might prefer something that, even though the mean might be higher, you might prefer a policy that has a lower mean, but also a lower variance. So you kind of avoid worse but rare outcomes. So that was the one for that one. The other area that I thought I'd mention briefly, and I think this is an area that we'll see more and more interesting developments over the coming years, is in model-based reinforcement learning. So this was another one from NeurIPS this month, sample-efficient reinforcement learning with stochastic ensemble value expansion. And they have an algorithmic approach that they get the acronym STEVE out of. And that was, I think, mostly Google Brain folks. So Jacob Bookman, Daniel Hafner, Joyce Tucker, Eugene Berto, and Honglak Lee. And it's another one, actually, where they're using this trick of using a bootstrapped ensemble to help us capture model uncertainty. And here they're actually using it in a model of the environment. So in addition to learning our policy and value, we're also going to be trying to learn about how the world works. So given a particular state and an action, what is going to be my what state will I transition into, and what will be the associated reward? And if you have a really good model of the environment, then you can learn much more quickly, because you can not only use the experience that you gather in the world, but you can also essentially simulate in your model what would happen if you did different things. But the problem, or one of the problems with that, is that if your model is inaccurate, then you can kind of run into all sorts of trouble. And so what they do in this paper, because they're learning this model with an uncertainty estimate, they essentially are able to use the measure of model certainty to figure out how far to trust their model, their environment model. So you essentially roll out your internal environment model to the point where you're essentially weighting how much you trust your model at different prediction depths into the future by how much uncertainty there is associated with that. And then at some point you end up bootstrapping. So it's kind of a neat way of combining model-based and model-free RL. So the other thing that, or one other area, and this is probably the last one that we'll touch on for today, I'll maybe just kind of give a shout out to some of the other ones that we probably won't have as much time to talk about.
Okay.
And that's this kind of trend of seeing sort of ways in which deep RL are being scaled up. So moving to kind of like these very large models, lots and lots of data, distributed training systems. So there's a couple of papers from this year that are doing that. So there was three from the ones that come to mind. There's three from DeepMind and one from OpenAI. So we had this paper, importance weighted actor learner architectures, Impala. And so the setup there is you have lots and lots of actors gathering experience. They send that experience to a smaller collection of learners, but even the learners can be distributed. And one of the kind of subtleties to that is in that kind of setup, the experience that comes from the actors might be a little out of date. So there's a little bit of off policy correction, but it essentially allows you to use extremely large batches and very big models and still kind of get through a reasonable number of model updates in a short space of time. So that's kind of one direction for scaling. The others, I'll just mention these, I guess, briefly. So there was a paper, distributed prioritized experience replay, and that's essentially a kind of value learning analog of the Impala stuff I just mentioned. So again, lots of actors generating experience, coming into a shared experience replay, and then learners pulling off on top of that. Another similar paper had an approach D4PG, so those all DeepMind, and then the OpenAI Dota. I think there's not a paper on that yet. I'm not sure, but they kind of detail it in their blog post. They have a similar scheme, I think, to Impala, where they have essentially lots of distributed workers generating experience, and then a small number of beefy, large batch learners pulling from the experience from the actors and generating parameter updates. And there's a couple of things there. As I said, one, it sort of like allows you to kind of crunch through a lot more experience, and in some ways, it's kind of just by scaling up in that way, it's able to address some of the inefficiencies of RL. So earlier we were talking a little bit about wanting to kind of pull as many different learning signals as we can out of the environment, particularly if reward is sparse or exploration is difficult. And there's sort of lots of different ways of tackling that. Some are kind of more algorithmic, but also just by scaling things up and pushing a lot more data through. That's another way of addressing that. And it also helps some of the kind of stability issues from the variance in the learning signals that you get in a lot of these environments. So again, I think that's another trend that we'll see just kind of being built on more and more. Similar to how in computer vision kind of things have been scaling up and up over the past like 5-6 years. So yeah, maybe if I'll just mention some kind of other interesting areas that we won't have time to dive into, but there's been some kind of interesting developments in hierarchical RL, multi-agent. There's been some neat work on sort of like leveraging different types of memories in agents, and also just the kind of folding in of the sort of broader advances from machine learning in general in terms of better ways of doing representation learning, generative modeling, all those other kind of techniques kind of feeding into DeepRL.
So just a quick review of the topics that we did cover here: imitation learning, unsupervised RL, meta learning, exploration, model-based RL, and scaling up. And those are just a few of the ones that you were able to think of. What would you say about the kind of the rate of growth of RL as a field?
Yeah, it's super exciting. There's a lot of difficult problems that we don't yet have good ways to solve, but there's a ton of creative solutions coming out.
Beyond papers, did any other kind of broader developments in open source or on the commercial side? Anything jump out at you?
Yeah, a couple. So I guess the commercial side I've tracked a little less of late. In terms of open source, there's a kind of background in terms of like the kind of continued development of both sort of like the TensorFlow and PyTorch frameworks and the supporting ecosystems.
Mm-hmm.
There've been a couple of things that I thought were pretty nice. So things like TF Hub, kind of having a kind of repository for models, and another kind of similar effort. So there's a couple of frameworks that I saw at Neurix that I like. So there's Dopamine, which is out of I think Google Brain Montreal, Lucid. So Dopamine is a kind of a nice way of making some of these. Yeah, with Dopamine, Lucid, and then there's also something from Uber, Model Zoo. The kind of combination of those is kind of nice in that I think it will maybe open up some opportunities to kind of play with DeepRL with a lower entry bar. So with the Model Zoo, they essentially have, I think, 3 or 4 different flavors of agent pre-trained on all the games in the Atari suite that you can just essentially download. And Lucid is this kind of visualization framework. And so with the two of those, you can start to play with some of these pre-trained agents without necessarily having to have the resources to train them yourselves, which I think is probably something that will be helpful for new people wanting to get into the field, to kind of get a bit of a warm start. And then also, I think in general, releasing pre-trained agents that people can build off of and poke is a nice trend, similar to some of the stuff we saw, again, sort of like looking back at computer vision with making some of the pre-trained models on ImageNet available. That helped a lot of folks kind of get a foothold there, and then also accelerated the progress in that field.
With these tools and with RL models in general, are the same kinds of things possible, like kind of taking off the last few layers of a network and fine tuning that same kind of transfer learning?
I guess it would depend on the agent, not so much in what's available right now. The transfer between different Atari games, for instance, isn't huge, but just in terms of having something that can get you started. So, for instance, the kickstarting stuff that we were talking about earlier in the conversation, if you have pre-trained agents that have some decent behavior, that can dramatically kind of shorten your experiment cycle time if you want to play with your own modifications of those architectures. I mean, eventually you might end up wanting to, not use any of that pre-training to kind of get a clear look at innovations that you're looking at. But if you don't necessarily have access to a ton of compute resources, then leveraging things that are pre-trained is a really nice way of making it more accessible.
Okay. So no direct transfer in the way we might see with CNNs, but you can use these agents to kind of get things kicked off.
Yeah, I mean, I think so. I guess transfer and RL is a whole interesting conversation that we could have on the side. But yeah, it would depend on what tasks you want to transfer to, and there's a lot of subtleties there. So even things like training and simulation, and then deploying in the real world, you see some transfer there. So I guess that's one place where you could kind of think of that as being pre-training and fine tuning. But yeah, I kind of think of that as a little differently than like I say, what this, or at least in its current state, the Model 2 is just focused on Atari. So it's more kind of entry level, but I think that's probably still something that, like I say, folks entering the field will find useful.
Okay, cool. And so given all that we've seen happen in 2018, what are your kind of thoughts and predictions on, what we'll see in 2019 and the near future beyond that?
Yeah, predictions are always tough. I think, yeah, a lot of the areas actually that I highlighted to me feel like they're kind of particularly active frontiers. So, yeah, I think we'll see more folks trying to come up with different ways of doing agent-based RL with more self-supervision. I think the kind of trends in sort of meta-learning, learning to learn, transfer learning, continual learning, so one agent learning to do many, many different things through a lifetime, are trends we'll see. Yeah, likewise, model-based RL, I feel like models have probably been a little less prominent in recent years. Sorry, like environment models. There definitely have been some papers that looked at that, but I feel like that's an interesting area for growth. So yeah, those are a couple that come to mind.
Any final thoughts before we wrap up?
Yeah, it's just I think a super exciting time for the field. There's kind of tons of groups, both from academia and industry, that are doing really great work. And so yeah, it's a super exciting time to be doing research in the field. And then also, I guess, through the broader machine learning community, there's a lot of great efforts in terms of just working to expand the pool of folks who can participate in AI research and who can kind of contribute to some of these problems that we're looking at. So yeah, I'm super optimistic for the future.
Well, Simon, thanks so much for taking the time to chat with us about RL. There's a ton of stuff here, and we'll try to get links to the various papers that you mentioned in the show notes. But thank you.
Yeah, thanks.
All right, everyone, that's our show for today. For more information on Simon or any of the topics covered in this show, visit twimlai.com/talk/217. You can also follow along with our AI Rewind 2018 series at twimlai.com/rewind18. As always, thanks so much for listening, and catch you next time. Happy holidays.